Hello, everyone, and thank you for joining our live session today. My name is Larissa. I'm an event planner at Reactor, joining you from Brazil. Before we start, I have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. The session is being recorded and will be available to view on demand here on the Rector YouTube channel within 48 hours. So keep an eye on the chat. We'll be dropping helpful links and checking for your questions. I will now turn it over to our speakers for today. Thank you and welcome.
All right, everyone. Hi, my name is Jonathan, and this is my co-presenter, Clement. I'm a software engineer at Microsoft, and Clement works at NVIDIA. And today we'll be going over how to serve production-grade LLM inference using open source and Kubernetes. So first of all, we'll go over the agenda. The first thing I'd like to introduce is our scenario, where we outline our problem, the solution, how to deploy using Kubernetes on AKS, our product Dynamo, which will handle the inference, and then we'll give a demo on what Dynamo looks like running on AKS. Lastly, we'll go over how you can get started on using this for yourself, and we'll take questions at the end. So our scenario is how to serve distributed inference for production-grade deployments, and these scenarios can run from e-commerce AI assistance to airline traffic rerouting. And these have several challenges. So one is that you have heavy prefill and lightweight decode, which wastes GPU compute. Another is how do you handle traffic spikes without over-provisioning, read computing shared context, or letting your KV cache and memory management get out of hand. And just to reiterate, the models have gotten a lot larger over the years. It takes a lot more larger context windows and a lot longer for it to generate responses. So the solution we propose is to use Dynamo and Kubernetes running on Azure. So the first thing is why Kubernetes and why Azure? The first thing with Kubernetes for AI is that we can leverage existing open source ecosystems and frameworks for scalable distributed deployments. So you don't need to reinvent the wheel when you have to run several hundreds of GPUs. For Azure, the managed Kubernetes service handles the cluster operation and admin responsibilities. So you don't need to worry about how to handle your control plane, how to deal with load balancing. This is all handled for you, and you can just worry about serving your AI applications. Azure also gives you GPU node pools with autoscaling, and there's also new managed storage solutions like Lustra, which is a file system designed specifically for high-performance computing and AI workloads. And it also has other managed metrics and observability services like Prometheus and Grafana. So Azure also includes several VM options. There's small nodes, which you can use to run test models for development. There's medium size models and large models like the 8x800 or H200 or GB200 nodes. I also want to call out the GB200, which is a new offering on Azure. These have 72 Blackwell GPUs in a single rack, and this solves one of the problems where communication between GPUs on the same rack is pretty fast, but communicating between nodes or machines is pretty slow. So by having these all on the same rack, we can significantly reduce latency. Next, we'll go over an overview of Dynamo, and I'll hand it off to Clement for this.
Thanks, Jonathan. Yeah, we'll move on to the next slide. So now let's talk about NVIDIA's Dynamo. So at its core, Dynamo is an open source inference framework, which is built for high throughput and low latency serving of generative AI workloads in a large distributed environments. So this is kind of built for scale, which you actually see in the real world enterprise deployments. Now, one thing I would like to clarify is where the Dynamo actually sits in the stack. So we do know that the common inference engines like the VLLM, TRTLLM, and the SDLang do a fantastic job in optimizing on what happens on a single GPU. But Dynamo works one layer above that. So it optimizes the system around those engines and how these requests that are coming in are getting routed and how the KV cache is managed and how the GPU resources dynamically shift based on the real time. So this is where Dynamo comes in and think Dynamo as more of a distributed intelligence layer sitting on top of your the regular inference engines you use in day in and day out. And yeah, to talk about KV cache, let me quickly explain because we are going to talk a lot about it today. So KV cache is all, but when a model processes your input, it generates some intermediate computation, and the results is what we call it as keys and value, and that is the KV cache. So storing and reusing these KV cache instead of recomputing them every time is one of our biggest levers in having like the improved efficiency. So whenever you hear the word KV cache, it is just like save computation so that you could reuse these computations intelligently whenever possible. So that is where Dynamo really helps, and Dynamo is composed of like multiple components together, so which you could plug in and use as needed, and you do not have to pick all of the components together. So but you can pick and choose what it is applicable for your particular environment, and each and every component gives its own performance boost on its own. So when it compounds together, you get to see like a significant performance increase. And yeah, Dynamo is like completely built for like a production at scale, where it it gives you like the end-to-end deployment life cycle, right from your assistance in getting your configurations right to the through the profiler, and providing like the fault tolerance and giving you that resilience layer. So Dynamo does it all effortlessly. And when you look at this diagram, this is like the complete architecture for the Dynamo, where your requests pass through the API server. So this is your primarily the entry point for all your user requests, and and if your current stack is already compatible with like the OpenAI API or the Llama Stack API, and Dynamo, you could just plug and play where it just works out of the box. You do not have to configure anything in specific. And yeah, once the request flows from the API server and it goes through the next layer, which is the smart router. So the smart router is not a typical load balancer, but it uses something called KV cache aware routing, which is specialized in insertion and eviction algorithms. So it gives a intelligent layer which decides where your request should go to in the corresponding worker nodes. And towards the left, you see the planner, which is continuously running throughout, and it monitors your um, like the access patterns, and it dynamically adjusts the resource allocation to keep your requests are optimized, and also you get to manage all your SLA latencies. And next, you see the disaggregated serving. So this is one of the critical layer for Dynamo, where you have different worker pools for context workers and generation workers. But yeah, we will dive deep into the disaggregated serving in the upcoming slides. And the other layers you see is the event plane, where it gives a little bit of the observability layer, and the KV cache manager gives you the management that handles all the KV cache management between like a different tiers of memory. Yeah, we will definitely talk about it a little bit in detail in the subsequent slides. And the final layer you see is the data transfer engine, so that manages the KV cache movement between all these worker nodes together. Yep. Yeah. So moving on, let's talk about disaggregated serving. Yeah. Let's move to the next slide. Yep. So let's break this down. So what exactly is disaggregated serving, and how the differences between the traditional and the disaggregated serving. So when the user sends a request to a language model, so what happens underneath the hood is two distinct computational phases. So the first phase is called the prefill, and the second is the decode. And during prefill, the model processes the entire input. So whatever you feed in as input, so, that is fed into the model, and it builds a contextual understanding of the request, and it generates the first token. So the metric we do care during the prefill phase is the time for the first token, what we call it as TTFT, how quickly we can get this first token back to the user. And the next phase here is the decode. This is where the model generates every subsequent token at a time until the response for your input request is complete. So the key metric that that is being tracked during the decode phase is the inter-token latency. So it is basically like how fast the tokens are being streamed back to the user. And yeah, now let's take a look between the difference between the traditional and the disaggregated serving. So when you take a look at the left side of the diagram, the traditional serving, so both phases, both the decode and the prefill, runs on the same GPU. So but there are difference in the way of computation and the resource demands for the prefill and the decode phase. Prefill is pretty much compute bound, which does like a lot of matrix multiplication processing, like inputs in parallel. But the decode phase has a completely different set of requirements, where it is memory bound, where it reads and writes data from the KV cache. So it has like a when we use the same GPUs for both prefill and decode, there is little bit of compromises that we do on the parallelism strategy, and that takes like a little bit of it when you are looking for some like a strict SLA and SLO requirements. And yeah, towards the right, we do see the disaggregated serving, and this is where prefill gets its own dedicated GPUs that is optimized for compute, and the decode gets its own dedicated GPUs, and once the prefill is done, the KV cache is transferred to the decode layer, and both of these prefill and the decode has can have like a different parallelism strategies to maximize the bandwidth. So this disaggregated serving will give you like a little bit more flexibility in optimizing cost and the user experience. Yeah, let's talk about a little bit of benefits of the disaggregated serving. So honestly, like the benefits are pretty much compelling. So the most immediate one is the independent scaling, because the prefill and the decode are now on separate GPUs. You could scale one based on what workload that your workload actually demands. Like when you see a surge in the input request, you could scale the prefill pool, but when you see that there is more decode that is required for your particular workload, then you could scale up these decode nodes in like, because like these are mutually exclusive, so that you could literally scale them up as needed. And yeah, the second benefit is around the parallelism strategy. So when they are coupled on the same GPUs, you are making like a compromises for both, but the disaggregation gives you freedom to apply the right strategy for each of these phases independently. And the other benefits comes to like on the SLA perspective, the fastest time to first token, the inter-token latency, and you could like find the right balance between your prefill and decode to get get the more optimized right balance for your traffic pattern. And Another good thing that often gets overlooked is um, when you have different GPU pools for prefill and decode, you can use different GPU SKUs, and you could make some cost optimization strategies based on the type of SKUs that you use for the prefill and the decode phase. Yeah, yeah. So you might be thinking that this all sounds great, but splitting and prefill and decode across different GPUs might introduce some serious complexity. And yeah, it is going to increase some complexity. So that is where Dynamo is going to help in. And the moment you decouple the context and generation on separate GPUs, there are three hard orchestration problems that surface simultaneously. And yeah, those are like a deeply interconnected problems. And we'll go over them one by one. First is the scheduling. So you need smart routing and planning that knows where your KV cache lives and in which worker pool the KV cache lives, so that whenever the request comes, you could redirect to the right workers and minimize the redundant computation as much as possible to keep the load balanced across your fleet. And second is the memory management. As the request volume grows, the KV cache also grows because like a GPU memory is finite, and it becomes a bottleneck at the memory level. So memory management is critical. We need to have like a tiered memory management structure so that we could offload the lesser used or like the not required KV caches to the lower tiers. And yeah, third is the data transfer. So whenever the context worker finishes the prefill, the KV cache needs to move on to the different generation worker pool, potentially using the fast NVLink, InfiniBand, and other interconnects. And any latency here definitely affect the performance. So we do have um, we do have the Nixel library that accelerates the data transfer between these KV caches so that all the nodes get the data transfer quite efficient. Yep. And let's talk about deploying the Dynamo itself. So far we have covered some of the core components of the disaggregated serving. So when we wanted to deploy Dynamo, it all starts with creating what is called the DGDR, the Dynamo Graph Deployment Request. And think of it as a single configuration spec that tells Dynamo everything that it needs to know about your deployment. So inside the spec, you choose what backend that you are going to use for your model, and like whether it is VLLM, SDLang, TRTLLM, and what model you are going to serve. So this all you could declare it upfront, and also something that you could configure as a part of it is the SLA target. So what are the SLA metrics that you are looking for as a part of this deployment? So you could all configure them within the DGCR, and from there you do run the Dynamo profiler. And here you have choice between like choosing two different strategies for your Dynamo profiler. One is the rapid profiling, where it uses a simulation to estimate the best configuration that your settings will need. It is like a 30-second quick profiling of your requirements. Absolutely no GPUs required during this rapid profiling phase. But in case if you wanted more of a thorough profiling where it deploys and benchmarks on a real hardware, we do have an option to do that one as well. So you could get the best hardware and the choices that you can pick. And the thorough profiling will give you detailed metrics with the highest accuracy of the configurations that could work for your workloads. And yeah, once the profiling is complete, the Dynamo automatically generates your optimized deployment. And this is where your model goes live with the right people and the decode configurations that are already in place. And once the model is deployed and it is serving the production traffic, and that is where the planner kicks in and it takes over in production. So it continuously monitor your traffic patterns for the workloads, and it monitors your GPU utilization in real time, and it dynamically adjusts your worker pools between the prefill and the decode nodes based on your SLA targets. And yeah, that is how this is like the entire workflow or the life cycle of how the Dynamo, right from your configuration stage to the deployment stage. And yeah, with that, I'll hand it over to Jonathan to walk you through the Dynamo profiler.
All right, thanks, Clement. So I'll go over the profiler, and the profiler is what makes the Dynamo graph deployment request, or DGDR, different from just a normal AI deployment. So this request lets you specify things like your SLA and your requirements based on your hardware, and it'll run a job where it generates the optimal configuration for you. So for disaggregated serving, for example, it can decide what the best split between the prefill and the decode pool, meaning which means how many GPUs do you have processing the input and how many are generating the output. So when you do the profiler, you can choose between the rapid or the thorough option. So the rapid is a fast option that just runs a simulation, and it'll use AI configurator, which doesn't require any real hardware. It just looks up your GPUs and your specs and runs a simulation that takes about 1 to 2 minutes, and it'll generate several outputs. It can choose which backend is best for you, meaning you can run the model on VLLM, SGLang, or TRTLLM, and it'll profile those and pick the best one. It can also decide whether you should be using disaggregated or aggregated mode. And aggregated mode is where you have the entire LLM flow from input to token generation running on a single GPU. So that's a situation where if you have, like, say, a small model, it doesn't really make sense to split it up. And then the other option is you can do the thorough profiling. So unlike the simulation where it just runs against known SKUs and models, this will actually deploy your model to run on your cluster. So this takes about 2 to 4 hours if you have a pretty large model, and it uses an AI perf tool to benchmark each of the possible configurations. So it'll generate, like, say, 5 or so, the top 5 configurations, and then it'll pick the best one and let you also choose which one you want. All right, next we'll go into a demo, and this will show the flow from the DGDR to the profiler to the deployment of the model. So let me switch over. Okay. So this will show the flow where you start from a DGDR and go through the deployment lifecycle. All you have to do is put in this input for your deployment request. So this is a request because it lets you specify what you want in a deployment, and it'll put in the request to have Dynamo fill in the blanks for you. So we have the model cached for Qwen32 that we're trying to deploy. We're using the AI configurator, the rapid search strategy, so we don't have to wait a couple hours, and we're using VLLM as our backend. We also set the workload specs with input sequence length to 3000 and output to 300, and we have our SLAs configured here as well with TTFT as 500 milliseconds and inter-token latency to 30 milliseconds. So what you're telling Dynamo is the model, your SLA, how fast you want it to profile, and if you want it to deploy automatically. So you're not writing Docker files, no resource calculations, no cluster management. And once you have this, you apply it, and you're pretty much good to go. You can go make coffee and deploy your e-commerce shopping assistant for this scenario. So once it's deployed, you can see that it's profiling and initializing, and you can go get lunch or whatever you want to do. But we can see what happens. So the profiler is first going to detect your GPU hardware, then figure out how many nodes you have and of what type they are. It'll start deploying the model after running the profiling simulation, and it'll generate a Dynamo graph deployment. So the deployment request generates the deployment, and it'll show you the profiling results for the optimal configuration. And if you set auto apply to true, you can have it automatically create the deployment for you, or you can set it to false where you just generate the deployment and you can see the result and do something with it. But we're going to go with the live deployment. So after it's generated the deployment, it deploys the model with a Dynamo deployment, and we can see that it shows to have disaggregated serving with 8 prefill and 8 worker pods. So right now it's just loading the model that we have cached in the cluster storage, and this will take a bit of time, so we can fast forward through there. But this will take about like 10 minutes for a model like Qwen32. But if you have better storage systems or a larger model, it could be shorter or longer. Okay, so this is when it's done deploying. We can see that the DGDR phase transitions to deployed, and we have our Dynamo graph deployment ready. So all the workers are healthy, and we can verify that through the status of the resources, but we can also check that the pods are running on the correct nodes. The front-end planner, decode, and prefill are working, and our e-commerce assistant is live. So you can port forward to talk to the service, where we go through the front end, and we can curl the OpenAI chat completion. We could also use the CLI as well for interactive chat. So that's a wrap on how the deployment scenario works for Dynamo. You specify what you want for your model, your SLA, and your requirements, and you hit go. It'll generate the best configuration, deploy for you, and you can go make coffee and do something else. But you have your deployment ready in one click. So next we'll go over what happens after you deployed your model. So once you've deployed the model, the Dynamo planner takes over. And this is what lets you keep auto-scaling your cluster and your model deployment based on the usage. So imagine you have, say, the e-shopping assistant where you have some traffic on normal times, but maybe on a Monday there's less people shopping, and on Black Friday there's a lot of people shopping. So this lets you determine, based on your actual usage of your model, how much we should scale up for the input processing in the pre-fill workers, and how much we should scale down as well for the pre-fill or decode workers. It could also reallocate. So if you have a lot more input processing you need, you can scale those up while leaving the decode workers the same. And we'll go into another demo where we outline another scenario. So this is one where you could have an AI assistant for dealing with airline flight disruptions. So once you have your model deployed, we can show the planner. So this is an airline mobile app with the AI assistant to help you deal with flight status checks, rerouting, booking, itinerary planning. And our goal is to maintain the SLA for quick response start and smooth response generation. So the current state is that once we have our model deployed and there's not much traffic, it'll scale down to just one pre-fill and one worker, decode worker. And the SLA planner will monitor your latency and auto scale to meet the targets. So we can see that our max GPU budget is 8. We poll every 60 seconds, and we try to predict as well what our input and output sequence is going to look like. So normal operations, usually it's just going to be pretty small queries like what's the status of your flight. And the planner is going to be scraping metrics through Prometheus. Prometheus scrapes it every 15 seconds, and the planner checks every 60 seconds. So we can see this countdown here, but we can fast forward past that. So the current planner metrics for light traffic on our airline mobile bot. And here's where we have our scenario. There's a major weather event approaching. Flights are delayed or canceled. And now your query is a lot more complicated than I want to check on my flight status. So now we have a lot of people where their flight is canceled. This person needs to get to New York for an important meeting by tomorrow. They prefer aisle seats, have pre-check, and also need to get their connections rebooked. So these responses are going to be much more detailed, and also the inputs are going to be a lot more detailed. We also have a huge traffic surge where we have, say, 200 people from the flight who just got kicked, and we see that they're all looking for a rerouting. So this is going to be we're going to simulate a stress test using AI perf to saturate the GPUs and get it to break the SLA. So the traffic pattern is we have 200 concurrent requests, long input prompts, long responses, and we need to track that we can restore our SLA. So someone's noticing that the app is being so slow, they're losing patience. Someone says they need to rebook now. And we're gonna find that once the interval readjusts, we'll see what the planner is thinking. Okay, so we see that the time to first token is way above target. They're waiting for too long. The inter-token latency is also too long. So we calculate a correction factor, and we figured out that we need to scale up. So it's provisioning more workers for prefill and decode right now. We're scaling up to 2 prefill workers right now. And to load the model, compile, and get it joined to the worker pool takes a couple minutes, depending on the size of your model. So now we have 2 prefill workers ready. The scaling's complete, so we can handle longer input sequences. And we can see that we have now 2 prefill pods and 2 decode pods. So we're scaled up. We can handle the traffic search smoothly, and we've restored our SLA. We can confirm the new configuration with the planner. We met the required replicas, and just to recap, we've handled an AI assistant with a normal traffic scenario. We've handled a flight disruption where there's a spike in traffic and a lot of unhappy customers. We see that puts a strain on the system, and Dynamo handles the auto scaling for that automatically. And the next part of Dynamo is the KV router, and I'll hand it off to Clement to go over that.
Thanks, Jonathan, for the great demo. And yeah, so we'll talk about the next component of Dynamo, which is the KV router. So let's take a look at what we have underneath the hood of the KV router. Next slide, John. Once you have like multiple worker nodes across your GPU fleet, a simple round robin or the load-based routing is what we call it as like a routing blind. So it might not give you the optimal results. So that is when the workers end up rebuilding KV cache for the same prefixes over and over again, and burning expensive GPU cycles. And it typically adds additional latency to every single request that is getting processed during uh, during like getting response back to the user. And this gets really painful in the workloads, particularly which has like the shared context. Think of something like a system prompts, multi-turn conversations, the agentic workflows, where we see the same prefix shows up for many requests. So the KV router, how this works is like it solves it by making the routing to the right worker nodes with a two signal decision process, and that is what it is illustrated in this diagram. So the input token flow into the KV aware router, which scores every available worker using something called a cost function. So the number of prefill blocks not at cached on the worker plus the active decode workload it has on the worker. So it is all calculated, and the router then picks the worker which has the lowest total cost. So here we do have like three scenarios: worker one, worker two, and worker three. Now let's look at each of these scenario. So worker one has two cache blocks, but it has 8 blocks that are not cached yet. So that means a significant prefill work needs to be done. Plus 10 active decode blocks already in flight for this node. So looks like this worker is already stressed for like the decode phase. Um, so when you look at the worker tree, it looks a little bit attractive at the first glance, where it has only 2 blocks left for prefill, right? But when you look at the decode block, where it carries like 9 active decode blocks, making it already like a heavily loaded, and it is like highly utilized worker. So when you look at the worker two, it has a sweet spot where it has like only 5 blocks to prefill, and it also have like a 5 active decode blocks that you could leverage. So when it comes to sending the request to the right worker, it is not always like a finding the worker with the best cache hit rate, um, because that might negatively affect the latency in a way. So the worker three has the best cache, uh, but when it comes to decode, it becomes a bottleneck where it could not process the request as efficiently as it could, and it will significantly increase the intertoken latency for this request. And this router avoids that by factoring in like both cache locality and also make sure the decode load simultaneously so that we get the uh, best optimized worker handles the request for the user. And as we know that the Dynamo is like a fully like a engine agnostic, so whatever the underlying backend that you use, so the worker automatically broadcasts their KV cache state to the router in the background. So that means like it all acts as async, and there is no instrumentation is needed. So the work out of so it works out of the box for any backend like a VLLM, Tensor, or TLLM, or SGLang. Good. And let's talk about the final component we have, that is the cache manager, the KV cache manager. So the KV cache router, though it does a great job in routing the request to the workers that already has relevant KV cache in memory, but that raises a natural, like a follow-up question: what happens when the GPU memory fills up? Because it has a finite memory, right? So when the GPU memory fills up, so how do we handle that one? So because like when you scale for multiple users, like 80, 100, 200, like thousands of users, so you are going to hit that ceiling of limitation in the GPU memory. So this is where the KV cache manager comes in. Look at the pyramid on the left. At the top, you have the GPU memory, which is the fastest, but it is most limited and the most expensive memory you have in the stack. And below that is the host CPU memory, and then the local SSD, and finally the shared network storage. So each tier going down is progressively cheaper and larger, but it is also a little bit slower. So the fastest is the GPU, and then like followed by the CPU memory, the local SSD, and the shared storage. So what this KV cache manager does is it intelligently moves these KV cache blocks across these tiers based on how frequently you access a particular KV cache. So the frequently accessed cache stays hot in top of the GPU memory, and the less frequently accessed cache gets offloaded down the hierarchy, freeing up the GPU memory for any new request that is coming through. And when that offload cache is needed again, it gets pulled back without having to recomputation. That significantly saves like a lot of time, because the recomputation phase might take a little bit more longer than like pulling up uh, from the different tiers of memory. And looking at the chart on the right, this is one of the experimentation that we have done at our end. So this was done for the Llama 8B model on NVIDIA HGX H100, where we had like 80 concurrent users across till 10 multi-turn conversation rounds, and the blue line is showing where you have the pure GPU prefix caching without no offloading into several tiers. And the green line metric shows how the Dynamo KV cache manager with the post offloading enabled. Now, notice something interesting here. So in the early rounds, the green line actually starts slightly below the blue line, so that is the small overhead for offloading mechanism, like initially kicking in. But as the rounds progress and you have like a multi-turn conversation progresses, and you see the GPU memory pressure builds, that is when the blue line climbs steeply, while the green line stays significantly flatter. But when you see around 9, the gap is like pretty much significant. You see like a 1.6x benefits in the TTFT, the time to first token. So the small upfront cost pays for itself like a many times over the scale as you go into like a mini multi-turn conversations. And yeah, the takeaway is pretty simple. The KV Cache Manager extends your effective cache cap effective cache capacity well beyond the GPU memory, what it can hold, without you paying for the recomputation penalty. But it gives a very better latency, lower TCO, and more concurrent users on the same hardware. And yeah, so that is how we leverage KV Cache Manager for effective use of the data transfer across different tiers of memory. And we do have another plugin also in Excel that is primarily helps with moving the cache between the different worker pools. For example, you want to move the KV cache between your prefill nodes or even between the prefill and the decode nodes. That is where the Excel plugin helps in accelerating these KV cache movement across the prefill worker. Yeah. And yeah, with that, I'll hand it back to Jonathan, who will share some of the resources that will help you to get started using Dynamo on AKS and, yeah, and play with it. Over to you, John.
All right, thanks, Clement. So, how do you get started? The first place is I would go to the Dynamo GitHub where you can see the repo if you want to ask anything from the maintainers. You can see the Dynamo docs as well as AKS deployment guides on how to run AKS with Dynamo. And to keep up to date with what's new on AKS, check out the engineering blog at blog.aks.azure.com. Thanks, everybody. And for now, we'll also take questions and answers for the rest for the 10 minutes we have left.
Hi guys, we have a question. How is Dynamo handling high load stability and deadlocks?
Um, I think that that's sort of what the planner is meant to do. So the profiler initially goes through and tries to come up with an initial configuration, but that's more of just an estimate based on either the simulation or on a performance benchmarking test. Well, once you actually start deploying the model, the planner is what takes over to decide to scale up or down based on the amount of traffic. And if you use a managed service like AKS, it can also not only scale up, Dynamo can scale up the amount of replicas, but AKS can also scale up the amount of GPU nodes you have. So if you run out of nodes and you have too many replicas you need, AKS can pick up on that and give you more GPU nodes as well.
That was the question we had from the audience for the moment. So if you guys have any last words, we can move on to finish the session. Thank you.
All right, sounds good. If you have any questions, please contact us at Jonathan Tong or Jonathan Tong at Microsoft.com. And Clement, what's a good way to reach you?
Yeah, please do email me, cpackhamisaac@nvidia.com, or feel free to connect with me on LinkedIn too, in case if you have any questions on scaling Dynamo or using Dynamo on AKS. Thank you, guys.
All right, thanks everyone.
Thank you. Thank you so much, Clement and Jonathan, for the session today. And thank you all for joining. Uh, Before we finish the session, we're always looking to improve your experience. So if you have any feedback for us, we would love to hear what you have to say. You can find the link to our survey on the screen or in the chat, and we'll see you in the next one.